All right, in this video, I'm going to give you another example on how to use neural networks in Python in order to classify things. In the previous example that I have provided the link in the descriptions, you can see how to use deep neural networks in order to classify images basically into different clothing items. In this particular example, I'm going to use the content provided in the chapter 4 of this book, Deep Learning with Python, in order to show you how you can use neural networks for basically text analytics. And specifically, what you're going to do is to use a data set of IMDb movie reviews and try to classify them into either positive or negative reviews. Before neural networks, people used to do sentiment analysis. So if there was a text and you wanted to see whether it has a positive tone or a negative tone, you basically use a dictionary of words that are pre-classified as positive or negative. So for example, the word terrible would have a negative value to it, whereas the word awesome would have a positive value to it. And then you'd simply count how many times positive words are used in a review and how many times negative words are used in a review. And then based on that comparison, you would classify the review as positive or negative. Here, we're going to use a completely different approach and using neural networks in order to automate that process. So the very first step is to import the database, and luckily for us, the database is already preloaded into Keras. So what we're just going to do is to say from keras.datasets, import IMDb. And just like before, what we need here is to have two data sets, basically training and testing data sets, and each of them should have the features and the labels. So what we're going to do is to say train data and train labels. So basically the train data includes the training features and train labels would include the training labels, and then test data and test labels. This would be the output from the imdb.load data. So what this line of code does is that it goes to IMDb, which is a preloaded function of library of functions here, and uses the load data in order to get the data that is already pre-existing in IMDb and puts it into the training features, labels, and testing features and labels. Now, one option that I'm going to use here is to limit the number of the words per each review. As you can imagine, some of the reviews are much longer than the others, and every word in every review is going to be used in our analysis. So to limit the resources required to analyze this data, I'm going to type in num underline words is equal to 10,000. And what this does is basically it cuts after the limit of 10,000 words per each review. All right. So from each review, it only imports the first 10,000 words. So let me just run it and see what happens. And it would take a few seconds, sometimes minutes, in order to run this, because basically it has to go find this data set over the internet and import it here. Now, I'm just going to type in train data and say 0 to show the very first observation in this data set. And you can see that there are a bunch of numbers that are meaningless for us. So what I'm going to show you now is to how to convert these numbers into meaningful sentences. But before we do that, let me just go over why these reviews are coded as words. So basically what it does is that every word has been translated to a particular number. So number 1 may be something, and number 14 may be another word, and number 22 may be another word, right? So there is a dictionary, again, within this IMDb library that maps each number to its corresponding word. So let's say that number 1 is equal to word this, number 14 is equal to word is, and number 22 is equal to good, and number 16 is equal to movie, then 1, 14, 22, and 16 would be equal to this is good movie, right? So what we are going to do basically in the next step is to go and get a hold of that dictionary that maps every number to its corresponding word and use that dictionary to translate these numbers back to their original words and therefore construct complete sentences and paragraphs. And to do that, what you have to do is to, so I'm going to delete this part because we won't need it, say word index is equal to imdb.get underline word index. All right, so this word index is what contains the index of all of these numbers and maps them to the corresponding words. And what I'm going to do here is to say reverse word index is equal to dict and say array. Let me make it a little bit nicer. Value and key for key and value in word index dot items. So here's how it works. It takes each pair of word and numbers from the word index and then swaps their places. So the number comes first and then puts these flipped pairs into a new dictionary called reverse word index. So now instead of saying apple and getting 1, you say 1 and get apple, right? All right, now that we have something that is going to reverse the coding for us, in other words, it gets each number and its corresponding word and reverses it back to its word and corresponding number, we can use that in order to decode these reviews. So the way that we do it is say that, okay, so decoded, let's say decoded review is going to be equal to a space and then join. So what you're going to say is say, all right, get this reverse word index for every number in a particular review and subtract it by 3. The reason that we do it is that this 3 offset is often used to skip the metadata entries like start of the text or unknown word in these reviews. So it basically shaves those meaningless words off and then also replaces anything that it cannot find with a question mark for all the observations that we have in our training data. So let's, for example, do it for the third review here and see what it says. So let me run this. Let me fix this. So should be working. I don't know why it's not working. Let me double check again. Oh, I forgot to put in get here. So reverse forward index dot get. And this should be like this. Why is it not working? All right, and so it reverses, and let's type in what is in decoded review. You see, it's still not legible, and that is because I have not put a space between the words. So if I do this, then you could see that it says this has to be one of the worst films of the 1990s when my friend and I were watching blah blah. So you see that this is the third review in the training data set, which is being decoded using this word index in a reverse manner, so that every previous number here has been mapped to a particular word. And remember, you didn't really need to do this. I just went through this in order to show you what is inside of these reviews, and basically to show you what we're working with, right? Now, the very first step before we can train any machine learning algorithm is to turn these integers, which are basically in our training data and test data features, into a set of meaningful arrays. And what we need to do basically is to create a humongous matrix. Each review is going to be turned into a series of zeros and ones. The way that it works is that we are going to basically create 10,000 variables, and those variables each correspond to a particular word in our dictionary. So there's going to be, say, a variable called this, and the value of this is going to be 1 if the word this appears in that particular location in the review. Otherwise, it would be 0, and so forth. So one other way to turn these reviews, which are in text format, to numeric format is to basically create that word to vector matrix, in which the vectors are going to represent each word, and their value is going to be 1 only in places where that word appears. So in order to automate that, we are going to create a function that does that for us, and then feed all of this training data sets into that, so that it can go through all of these and turn them into that humongous matrix that I just explained. So to do that, I am going to define this function. So I'm going to type in define, and it will be called vectorize sequences. So vectorize sequences, and this function will have 2 parameters, sequences and dimension, which I'm going to put equal to 10,000. Now I'm going to define what's inside of this matrix. So basically, the first parameter, the sequences, is a collection of sequences where each sequence itself is a list of integers, which are corresponding to these word indices. And the second parameter, dimension, which we've put equal to 10,000, this represents the size of the vocabulary that we're dealing with. And if you remember, I said that we're going to import only 10,000 words in each review. Now, here is how we are going to set up the base matrix. we're going to say results is equal to np.zeros, and this is a numpy function that basically turns everything to zeros, and then it would be length of sequences and dimension. So I'm just going to copy and paste because I'm very prone to typos. So this is going to be our base matrix, which just includes only zeros, right? Now we have to start filling this matrix, right? What do I mean by filling this matrix? It means that we are going to put ones in places where that corresponding word appears. So we're going to say for I, and we say sequence in enumerate sequences, results I and sequence is equal to 1, and then return the results. So as we loop through each sequence, we take every word in the index present in that sequence and then set the corresponding column in our matrix to 1. This marks that a particular word is present in the sequence, right? And then finally, with the returning of the results, after marking all of the words present in our sequence, this matrix is basically complete. Each row now effectively represents a sequence with a simple binary flag for the presence of the word. All right. So if a particular word appears in the review, the corresponding column of that word is going to show 1, otherwise 0. So for this review that you're seeing here, if there is a column for the word this, the value of that column for that particular review is going to be 1. And if, say, there is a column for the word Python and that doesn't appear in this review, then the corresponding value for that cell or in that row, in that column, is going to be equal to 0, indicating that the word Python doesn't appear in that review. And then once we have defined this function, we can basically have it go through all of our observations in the train and test data sets. So I'm going to say copy the train data, and basically I say the train data is going to be input to my newly defined vectorized sequences function, and the output is going to be stored in something that I'm going to call xtrain. I'm going to use capital X for this. So xtrain, and I will do the same here, xtest is going to be vectorized sequences of the test data. So basically, with this, the train data and test data that included arrays of numbers are now going to be turned into matrices that only include zeros and ones, right? These are word to vector matrices. And okay, I have to define numpy first. So I just have to say import numpy as np, and now it runs. Perfect. So This was the decoded review for the third observation in the train data. So the corresponding thing for you to just see how it looks like is going to be x train 2. And as you can see that we have just a bunch of zeros and ones representing the same review again. Now this is great for us because we can use that to train our neural networks with just a little bit more cleaning before we do that, but it's quite ready now. All right, once we have converted the features data set into arrays, we have to do the same for the labels data set, basically turning our labels data sets in train labels and test labels into arrays. And the way to do it is super simple. So what I'm going to do is to just say, all right, y train is equal to np.as array and give it the train labels data set dot as type float 32. And I just do the same thing for the test labels as well. So y train and y test, and I have test labels. So the very first thing here is that the conversion to array, the np.asArray, this function basically transforms whatever format the labels are currently in, just be it a list, a tuple, or something else, in a well-structured NumPy array, which is a format preferred for numerical computations and feeding into algorithms. Now, the other part, this type, as type float 32, this is used to ensure that the data type of these labels is float 32, which is a type of a floating point number that's a bit less precise than the default double precision float 64. And the reason that you're using this, despite the fact it's a very small detail, is that it requires much less memory and can lead to much faster computations, which is particularly useful in machine learning when dealing with large data sets or performing many calculations where the precision in those calculations may not necessarily be what you're looking for. All right, now that we have everything transformed into the format that is appropriate for machine learning training, we can go ahead and basically build our model. And remember, we're going to design a sequential neural network. So we say from Keras, import models, and from Keras, import layers. And by the way, if this part of the code does not run for you, make sure that you have correctly installed Keras and TensorFlow. I've put the link in the video that walks you through how to do it in the description. So make sure that you watch that and have this properly installed before you run this. So before I type the code, let me just explain what I'm going to do. I'm going to create a network that has one input layer. What is that input layer? That input layer is going to have 10,000 input nodes, each node representing a word, right? Which is a 0, 1 right now. Then there are going to be 2 middle layers. Each of them would have 16 nodes. And both of these middle layers are going to be dense, meaning that there is going to be a connection between each of those 10,000 nodes in the input layer to each of those 16 nodes in the first middle layer. The first activation function going from the input to the first middle layer is going to be ReLU, and Then there is going to be another middle layer, again with 16 nodes and an activation function of ReLU type. And once the data is passed through these two middle layers, it's sent to the third layer, which is going to only have one node, and that output is basically what we are looking to. And therefore, we're going to use a sigmoid activation function to turn those continuous values into a value between 0 and 1 for us, representing the probability. So here's what I'm going to do. I'm just to say like model is equal to models.sequential. Why sequential? Because, you know, this is the type of the model that you're going to use, right? And the models is the library that I just imported from Keras. And then I say, all right, model.add layers.dense 16, and activation is equal to ReLU, and input shape is 10,000. Okay, so that is going to be the first middle layer. Now the second middle layer, again, going to be model.add layers.dense, again 16 nodes. Activation is again equal to ReLU. You no longer need to define the input because the input is the previous layer. Then you say model.add layers.dense, and remember this is the output layer, therefore we only have one node here, and activation is going to be sigmoid. All right, now that I have defined the shape of the network, I have to basically tell Python how to compile it. The optimization that we're going to use here could be very different. In this particular case, we're going to use the root mean square propensity here. So RMS prop is going to be our optimizer because we have a binary model. The review could either be positive or negative. There are only two cases. The loss function is going to be binary cross entropy, and the metric that we're going to observe is going to be accuracy. So I'm going to say model.compile optimizer is equal to RMS prop, and loss is binary cross entropy, and metrics is going to be accuracy. Okay. All right, we're now actually ready to run our neural network. However, before we do that, I want to set aside a portion of my training data set to monitor how well the model is doing before I run it on the test data set. So to do that, I'm just going to say xval is equal to xtrain, and then 10,000, all right? And then I say partial xtrain is going to be xtrain 10,000 onwards. And I will do the same thing for my features data set. by just changing the X to Y. So when I want to create my validation data set, I start by carving out a portion from our training data to use as the validation set. And basically, this is what I've done. I've taken the first 10,000 observations from the X-train data set and assigned them to the X-val, right? So this X-val will be functioning as our validation input feature. Similarly, I've taken the first 10,000 entries from the Y train and put them in the Y val data set, and this will be our validation target. Now, we take everything beyond the first 10,000 entries in X train and call it partial X train, right? So it's from the observation 10,000 onwards, whatever remains in it is being put into partial X train, and the same thing for Y train. So whatever remains after the 10,000th observation is put in the partial Y train observation. And in a second, you will see why I did that. So let me see what happened here. Y train. Okay, you see, this is the problem. Train labels, Y test. This is running, right? And X train. Oh, X is capital, so it should be capital here as well. X train, Y train, Y train. All right, now it runs. Perfect. So what I'm going to do here is to say model.fit to run my model, and what is going to be my input data set, the features data set, remember, it's going to be the partial X train. What is going to be the labels data set, the partial Y train. I'm going to run it 20 times, so epochs is going to be 20 times, and the batch size, every time I'm going to run 512 observations. Oh, the reason that runs here. Okay, so batch size 512, and I would say validation data is equal to my X val and Y val. So this will run my model 20 times. Every time it will feed 512 observations into the algorithm to go over all of the nodes in the layers in the neural network. And it will calculate the accuracy for me as I've defined here. And not only it will do it on the X-train, Y-train data set, but it also will do it on X-val and Y-val data sets, right? And in order to keep a record of everything that happens during each run of those 20 runs in my model, I'm going to store them in this history objects and then run my model. Validation data. Why is it not running? Oh, it's because I forgot the comma here. Let's see what is defining here. TensorFlow constructed its shape. Okay. Let me check it out. Okay, I think I figured the problem, and that is in the definition of the layers. Here I have incorrectly typed in 0 for the input shape of the first layer. So if I remove that and then run the model again, it should run. Where does it come in from? Let's see if it runs now. It takes a while. There we go. Yep. It starts running. So because we have asked for 20 passes through the data, it goes from 1 to 20, and in every pass, it calculates the loss and accuracy, both for the training data sets and the validation data sets. And one thing that you would notice is that the accuracy is quite high for the training data set. However, the accuracy for the validation data set is not necessarily that high. So it starts from 86%, and it actually at some point goes down to 85%, and then hovers around 85% around there. So what it basically shows that is running the neural networks for too many times is not necessarily good, because what happens is that the algorithm is going to memorize the special shape of the training data, which is good for accuracy in training. However, those patterns that the algorithm has memorized in the training data set may not necessarily appear in the testing or validation data set, and therefore the model would underperform in testing despite the fact that it overperformed in training. So this is a classical case of overtraining an algorithm. And it seems like the highest validation accuracy actually happens at the 4th time. So a very amateurish way of improving or fine-tuning this algorithm is to change the number of epochs from 20 to 4, where you get the highest accuracy in the validation data set. And once we have got the model trained, we can actually use that to do some predictions. And it is super simple. You can say model dot predict x test. So let me see how I typed in my x test here. Y train x test. So once I run this, what happens is that the model would take the input features of the test data set and create the prediction data set, which is going to be basically a set of probabilities for each of the observations in the test data set. And it takes a while, again, because there are 782 observations in the test data set that have to go through this prediction. So there are 782 review texts. Each of them could be a paragraph or more that have to be evaluated as whether positive or negative. And these are basically the results. And as you can see, that these are quite useless for us. because we want to have 0 and 1s. So what we are going to do is to save these into an object called predictions. So I'm going to say predictions is equal to, so let me copy and paste this here. So predictions is going to be equal to model.predict, and then I'm going to turn this into binary predictions, because these are probabilities. All of these values are between 0 and 1. Why? Because we use the sigmoid activation function as the in our last output layer of the neural network. So these are all between 0 and 1. I want to turn them into zeros and ones. So I'm going to say binary predictions is going to be equal to, well, if predictions is larger than 50%, it's going to be 1, otherwise it's going to be 0. So as type int. And then once I have them as 0 and 1s, then I can actually go and compare them with the 0 and 1s that I have in my y-test data set, which is the actual outcomes. And what is the best way to compare how our model is performing is to do a confusion matrix. So I say confusion matrix is equal to confusion matrix. What am I going to compare it again? It's my y-test, just to make sure that I have done it correctly. So this is the y-test, which is the true values of the sentiments of each review. So y-test is going to be compared against these binary predictions, and then print this confusion matrix for me. And because I'm using the confusion matrix, I have to first import it. So from sklearn dot metrics import confusion matrix. And again, I have multiple videos in which I walk you through how to create very beautiful confusion matrices. In the interest of time, I'm not going to do that. I'll just put a link in the descriptions below for you to see how to visualize these confusion matrices better. But I'm just going to just print it down here so that we can have an idea of how well the algorithm has done in terms of predicting whether a review is positive or negative. Give it a few seconds to finish. And this is basically our confusion matrix. So there are 10,773 reviews that were positive, and the algorithm correctly classified them as positive, and there are 10,000 reviews that are negative, and the algorithm has classified them as negative correctly. And then the false negatives and false positives are 2,201 and 1,727. So overall, the algorithm is doing pretty good. I would say its accuracy, just by looking at these numbers, is 4/20, which is about 80%, even a little bit higher than 80% accuracy in predicting the tone of a review into positive or negative. Now, this will end the video. I will put the code on GitHub and put the link down if you want to run it for yourself. A good practice would be to try to visualize the confusion matrix here. calculate other measures of accuracy, such as recall and precision for this algorithm. And if you're doing exercises at home, what I recommend that you do is to compare this algorithm with other algorithms that we have already gone through and see, if those algorithms will give you better results or not.